So good evening. Let's start with the next topic over here, the smoothing filters. Okay, so they are also regarded as the averaging filters, right? So we will be discussing how FIR filters can be used to design this different types of smoothing filters, and later on we will also look into how FIR filters are used for designing this derivative filters. Okay, so these two are the very common types of filters. So these two are the very common types of the filters that are being used very commonly in various applications, say whether biomedical applications or any other applications. Okay, so what are the functions of the smoothing filters? The first thing is that it reduces high frequency noise. Okay, so smoothing filters, in one sense you can say that they are low pass filters. Okay, they are low pass filters and they help us in reducing the high frequency noises. Okay, so the outcome is that we get a more cleaner and more stable signal as the output. Okay, second thing is reduce quantization noises. Okay, we have already discussed about the quantization process. In the quantization process, what happens is that when you are quantizing the sample, you are basically rounding off some values. So the signals what you will be getting, they will be not smooth and you will be having a staircase like signal tracing. Okay, now once you get that staircase like signal tracings, you have to apply the smoothing filter so that you get a smoothened signal. Okay, so that's how it helps us in reducing the quantization noise. Then comes the reduce motion artifacts. What are motion artifacts? In many of the these lab classes we have seen that we are placing electrodes at the surface of our body. Okay, so this type of signal acquisition, it is called non-invasive signal acquisition techniques, right? Now we are placing the sensors or the electrodes over the surface of our body. Now due to this reason, what happens, there are various types of movements the patient may move. Okay, while you are breathing, your electrodes may move. Okay, now due to this movement of the electrodes, what happens, we will have some type of noises into the body, into the signals. So these noises, they are basically very high frequency noises and they are regarded as the motion artifacts. Okay, so these are basically the unwanted signals which get into the signal, that get into the main signal due to the movement of the electrodes over the body surface. Okay, so these smoothing filters, they help us in getting rid of this these motion artifacts. Okay, then smoothing of the data. Smoothing of the data, many times we use it if there are any say what you call there is many unwanted signals, high frequency noise signals. Say for example, in most of your class these things, if you see, many would be having a cluster of say signal components or the marks, so say within a certain limit, say 22, 25 or 26. One or two students may be outside this range, say some may get 30, some may get say 11 or 12. Now if you do the averaging of this one, so it will bring the signal nearer to your actual values. Okay, actual average things, right? So this thing, it is regarded as the smoothing of the data. Okay, so I will give you an example over here. Suppose we are having this time unit n, and this is the number of students that are increasing entering into the class. The time unit, it increases by 0, 1, 2, 3, 4, 5. Okay, at the 0th instance, when I already entered, when I am entering into the class, say two students, they are already present. Okay. Then the next moment, three students enters together, then two students enters together, then again one student enters together, then at the fourth instance, the time index, three students enters the class, and lastly, at the fifth time index, two students again enter into the class. Now, if what is this? This is nothing but this number of students is nothing but the amplitude values, okay, and it is varying with respect to the time. So we can consider that the students entering into the class with respect to time as a signal component. Okay. Now, if I want to find out at 0th instance how many number of students were present, okay, average students, we have to find out, and I want to take three time instances into account, then what I will do, I will take 2 plus 0, that means minus 1, there were 0, and minus 2, there would be 0 divided by 3. So I get that if I apply a filter, this smoothing filter, then I will get at 0th instance 0.66 number of average number of students they were present. Then as I go into the first time index, so I get 3 plus 2 plus 0, 1.66. Then what happens at the second instance? I have 5 plus 3 plus 2 divided by 3. So 3.33. Then at third time instance, 1 plus 5 plus 3 divided by 3, it's 3. Similarly, at fourth time index and fifth time index, we get 3 and 2 correspondingly. Now, if you look at the initial stages, what was happening? We were getting readings which were much smaller as compared to the actual average value that we should be expecting. So, why this is happening? Whenever you apply any filter, it will need some time to get stabilized before it starts giving you stabilized outputs. Okay. So, like any instruments, suppose you want to use UV visible spectrophotometer or any other instrument you want to use, you need to give the instrument a time during which it gets stabilized, right? Now, for the filters also, while we are using it, depending upon what is the specification of the filter, we need to give it a stabilization time, and during that time we should not analyze the signal. Okay, we should not take those signals into account while we are doing the analysis. Okay, because as you can see over here, that would give us an incorrect result, and that result can misinterpret your results. Your inference would be wrong. Okay, so however, if you look into the second instance, when we are having all the three components and we are getting we'll be getting the average in a proper manner. So what happens over here? If you see at this location, we are having a very high value. However, if you see the result, it is nearer to the average values. Similarly, at the third instance, if you see the number of the students, it has come down drastically. That is also again in noise. Okay. So, but if you look into the average, it is 3. Okay. So this is how the smoothing filters, they can help you in getting a smoothened data. If you see, if you eliminate these two readings, if you see, you are getting nearly a constant reading and you are getting a more stable reading. Okay. So in this way, we can uh, smoothen the data using the smoothing filters. Okay. Now basically, what we are doing, basically, if you see, we have designed a simple moving averaging filter. We have designed a simple moving averaging filter, and it is a 3-point moving averaging filter. Okay. It is a 3-point moving averaging filter. So what we have done, yn equals to 1 by 3 xn current instance plus 1 instance back plus 2 instances back. Whatever would be the values divided by 3 would be your this thing, your moving averaging filter output. So you change the value of n equals to 0, 1, 2, 3 and you will be getting the outputs. So if I say you find out the transfer function of the system, you should be able to do it, yes or no, right? So what you will be getting, y of z equals to 1 by 3 xz plus xz z inverse plus xz z to minus 2. Okay, then what would be the transfer function? One plus z inverse plus. Okay, if I ask you implement this filter, you should be able to do it. If I ask you find out the amplitude response, you should be able to do it. If I ask you find out the phase response, you should be able to do it. Now if I say find out a 5-point averaging filter, you should be adding 2 more coefficients into the system, right? Now if you look over here, the types of the smoothing filters that are used, they are basically moving averaging filter that you have just designed, then exponential moving averaging filter, in short we call it as EMA. Okay, herein more weights, more weight is given to the recent data points and it provides a smoother response to the recent changes. That is the important thing. It provides us a smoother response to the recent changes. Okay. Then I also told that low pass filter, because it is having a smoothing effect, so it is removing the high frequency noises. These are basically low pass filters. Okay. And lastly, we have Gaussian filter. So in the Gaussian filter, so what happens is that your this filter coefficients values, they should be in the Gaussian, what do you call it should be in the Gaussian way. Okay, so what I mean to say is that if you are having h of n, so it would be for a 3-point Gaussian filter, it should be 1 to 1. Okay, for 5-point system, it should be 1 to say 6 to 1. It may be also in that way, so it should be 1 2 3 2 1. It all depends on how you want to design the thing. Now so the 5-point system, if you see, you can design in either of these two methods. In the first case, what happens, what should be this normalizing point? There should be a constant multiplier. Okay, in this case it should be 1 plus 2 plus 1. That means we'll be having 1 by 4. Okay, in the second case 3 plus 3 6 plus 3 9. So it should be 1 by 9. In this third case it should be 3 6 9 3 12, 1 by 2. Okay, so why we are giving these values? We are giving these values because if you just try to multiply the signal with these components, it may go out of bound. So we are multiplying the signal with some coefficients. Okay, so suppose we have a signal 1 1 1 1 1 in this way, you are having say 5 times. Now if you suppose over here we are taking this thing xn equals to 1 1 1 1 1. So when I will be processing it, what will be happen? What you will be getting? You will be getting 9, because 1 multiplied by 1 plus 1 multiplied by 2 plus 1 multiplied by 3 plus 1 multiplied by 2 plus 1 multiplied by 1. So you add it, you get 9. Now if you do not give this constant multiplier, which is basically regarded as the normalization factor, what reading you will be getting? You will be getting a value of 9, which is incorrect, right? So this normalization multiplication factor should be included over here. Okay, so you have now understood what is moving averaging filter, what is exponential moving averaging filter, low pass filter. These are nothing but just by placement of the poles and the zeros. We have already discussed how to design a low pass filter, but they may or may not follow the equations that we have discussed in moving averaging filter or the Gaussian filters, and at a later stage we will be discussing about this exponential moving averaging filter. So, moving averaging filter equation, we have already discussed about this one. 1 by n summation of k equals to 0 to n minus 1 kn x of n minus k. Okay, you have just designed, and this is just the mathematical representation. In the next case, what we have is that exponential moving averaging filter. Okay, exponentially moving averaging filter. So here we have yn equals to alpha of xn plus 1 minus alpha y of n minus 1, y of n minus 1. So it is basically taking information from the previous instance. Okay, it is taking information from the previous instance, and if you look, it is giving more weightage to this alpha if your alpha value is high. Okay, so it is a type of weighted moving average filter. Okay, applies more weight to recent samples, allowing for more responsiveness to the changes in the signal. The recursive formula, it is given by this equation, and alpha, it usually varies from 0 to 1, and it controls the smoothing of the signal component. Okay, provides smoother results while giving more importance to the recent data points. So Gaussian filter we already discussed. Okay, then low pass filter, it removes high frequency components and passes the low frequency components, thus smoothing the signal. Okay, so operation, it can be implemented using FIR or IR filters designed to suppress frequencies above a certain cutoff frequencies. Effect reduces noise by eliminating high frequency variations, preserving the overall shape of the signal. Okay. Now applications of the smoothing filter in biomedical signal processing. It can be used in ECG signal processing. It can be used in EEG signal processing. Okay, over there, if you see, it can help us in reducing noise. It can help us to enhance the QRS complexes and reducing the baseline wandering. Okay, EMG signal processing, it helps us in getting the smoothing of the EMG signals to study muscle activity without noise interference. Okay, so what happens over here is that, if you must have seen in EMG what happens, you are getting some signals like this. Okay, so usually, do we analyze the signal in this format? Usually we do not analyze this in this format. What we do, we square it initially, so that these bipolar signals, they get unipolar signal. How do you do it? Either you do x square, or you can apply modulus of x operator. Okay, so once you have got this thing, then we can apply this smoothing filter to get the envelope of the signal. So after applying the smoothing filter, you will be getting an envelope like this. Okay, now you can use this thing, because if the amplitude of this envelope is increasing, that means the strength of the EMG signal is higher. That means more number of muscles are being recruited. So in your last class, you have seen that when we are increasing the weight in our hand, there was an increase in the strength of the EMG signals. So you will find that there would be an increase in the amplitude values of this envelope. Okay, so it can be used in pulse oximetry. It can help us in smoothing the oxygen saturation signals, so that you get more accurate readings. Then in the blood pressure monitoring also, it can be used to eliminate the transient noise in the blood pressure waveforms. Then in the respiratory signals also, it can help us in smoothing the respiratory signals in the spirometry and respiration monitoring devices. So basically, in whatever the things we are saying, what it is doing, it is trying to eliminate the high frequency noises or any noise component or signal components which might have been included into the signal due to some unforeseen reasons, okay, for any particular instances. Okay, so whatever the signals you see, smoothing of the MEG signals, smoothing of the ERG signals, smoothing of the motion signals. So everywhere it is basically smoothing the signal response, and it is giving you a proper uh, uh, result wherein the effects of the high frequency noises, they are being reduced. Okay. Now, next type of filters that is quite commonly used is the derivative filter. Okay, so unlike smoothing filter, which rejects the high frequency noises, derivative filters, it allows high frequency components. Okay, noise, we are saying high frequency noises because we don't want them, but in many cases you may have high frequency components that needs to be amplified. Okay, so in that case what we will do, so in those cases the derivative filter, it comes into play. Okay, so what are the applications of the derivative filters? Edge detection, it can be used in feature extraction, and it enhances high frequency components. Okay, so what is an edge? How do you define an edge? How do you tell that this is the edge of the tip? What boundary? If you take an image from here, what you will see? There will be a constant signal amplitude levels, and at this edge there would be either drastic fall or drastic increase in the intensity. Okay, so in a plane background, when there is a drastic increase or decrease in the amplitude levels, so that is called edge. So what is this? This is nothing but a high frequency component. Edges are the high frequency component. So when we talk about the edge detection, we are basically detecting the high frequency component. Okay. So this is where the derivative filter comes into play. Okay. It may be a first derivative or a second derivative filter. The first derivative filter, it is a simple difference filter, xn minus of x of n minus 1. Okay. So the important thing over here, if you see, is that in derivative filter, if you see the coefficient over here, it is 1, this is minus 1. Okay. In higher order filters, if you want to design, you will see at a later stage that the same thing applies in the higher order filters. So there would be a gradient. So from plus to minus, we will be moving. Okay, from plus, the coefficients, for the coefficients will be moving from plus to minus. So there is a formation of a gradient, and hence derivative filters, they are also regarded as the gradient filters. Okay. In the second derivative filter, if you see again 1, x of n minus 2, 1. If you see the coefficients, 0. Addition of coefficients, 0. Addition of coefficients, 0. 0. Okay. So this second derivative filter, it highlights where the slope changes, often used in edge detection for images or peak detection in 1D signals. So first derivative, then second derivative. So filter response, first derivative response, sensitive to small sharp changes in the signal, okay, which is basically the high pass behavior, high pass filter behavior. Second derivative filter response, even more sensitive to rapid changes, often emphasizing high frequency noise as well as key signal transitions. Limitations, derivative filters can amplify noise. As I told you, most of the noises, they are high frequency noises. So especially in the case of high frequency noise. Okay, so if you are having high frequency components, say for example in the EMG signals, and over there if you apply these derivative filters, then what might happen is that if there are any noises in your EMG signals, they may also get amplified. Okay. So common derivative filters: Sobel filters, Prewitt filters, canny edge detection filters. Okay. Key benefits of the derivative filters: feature detection, edge detection, and in some cases uh, you may have this noise amplification. While they emphasize the rapid changes, they can also amplify the high frequency noise, which often necessitates using the smoothing filter. Okay, because noise amplification means, as I told you, you are having this high frequency component. When you apply the this smoothing filter, you are basically suppressing the high frequency components. If they are noise, that's fine. However, if you have some high frequency components within the signals, if they are getting suppressed, then this high pass derivative, derivative filters, they can allow the strengthening of those signal components. Okay. Challenges and mitigation: noise sensitivity. They are very highly sensitive to noise, especially in biomedical signals that are often noisy. To mitigate this, smoothing filters, Gaussian or low pass filters can be applied. यहाँ पे जैसे I told, for the smoothing filter you apply to overcome the reduction of the high frequency signal components, you apply the derivative filter. In the same way, in the next thing, you apply the smoothing filters. Okay. So applications: ECG signal processing, EEG signal processing, EMG signal processing. So here, if you see, uh, useful in QRS detection, QRS complex, it is a high frequency signal, right? Then talking about epileptic seizures, in epileptic seizures you get high frequency signals. Then EMG signals you have seen the spikes, they are basically high frequency signals, right? So whatever the things you will be seeing over here, you will find that the signals what you are trying to extract using the derivative filters, they are basically high frequency components. Say for example, detect systolic peaks. What is systolic peak? Systolic means when there is a contraction of the heart muscles. So it is basically there is a sudden increase in the blood pressure levels. Okay, so what is that? Again, nothing but your sudden change in the amplitude level, and it is nothing but your high frequency components, right? So whatever the examples you will be seeing, whatever the this application you will be seeing, everywhere you will see that there are some high frequency components associated with the biomedical signals, and hence and you want to extract those high frequency components, and hence the derivative filters they are being applied. Okay, so same over here, you can just go through this. Now some examples of FIR filters, again smoothing filters: 3-point averager filter we have already discussed. Okay, implementation, you can implement it. Hanning filter, it is basically a कौन सा type of filter? If you look into the years, Hanning filter, what kind of filter it is? Derivative कहाँ से है? All are plus. अरे Gaussian filter, Gaussian averaging filter ना? हाँ, 1 to 1. So it is a Gaussian distribution. So it is a Gaussian filter. Again, if you see what I told, in this thing you will be having the summation will be one summation of the coefficient, it will be divided in the filter response 1 by 4. So distribution is Gaussian 1 to 1 and division. So it is a smoothing filter. Hanning filter, this Hanning filter, it is a smoothing filter, and it is applying a Gaussian distribution thing, right? Again, you can find out the amplitude response and the phase response of the filter. Okay. अगर मैं बोलूँ 0 pi by 4, pi by 2, 3 pi by 4, pi में निकालना है. You just have to put the values of omega and you have to find out the amplitude response and the phase response. Okay. Now least square polynomial smoothing effect. As the name suggests, it is a polynomial thing. So it applies a polynomial stuff. So basically we are having these tap pits and there is this L factor. This is not the length of the filter. This is the L factor. L factor is nothing but, if you see, there are 1, 2, 3, 4, 5 coefficients. So you get basically ये L is equal to, this is n minus 1 divided by 2. This L factor is equal to n minus 1 divided. You can say alpha, but it is L factor. It is not that length of the filter. Okay. So in least square polynomial smoothing effect, if you see minus 3, 12, 17, 12, minus 3. Okay. So again, if you try to add this up, so you will get that 1 by 35. Similarly, for when L factor is 3, you have to put this what you call coefficient, filter coefficients, and similarly for L equals to 4, L equals to 5. Okay. यहाँ पे this is the generalized form of the implementation, and then what you have to do is that you have to just remember these things. इसका और कोई उपाय नहीं है. You have to remember the stuff. Then coming to the notch filter, suppose you are having fs equal to 180 samples per second at a 0 at 2 pi by 3, remove 60 hertz line interference. Okay, line interference. So if you use this filter, that means if you place uh, this 0 at z equals to minus 0.5 plus minus j 0.866, you will be designing a notch filter which will be able to eliminate the 60 hertz component. Now if I ask you to design a 50 hertz this notch filter, you should be able to do it. Okay, how will you do it? You will see how will you do it. Okay, we will see at a later time. So this is how you implement the filter. Okay, now derivative, see simplest filter, 2-point difference. Okay, this is 3-point central difference filter. So this is the simplest filter. Now the problem is that if you look into the pole zero plot at high frequency component, there is no zero. Okay, so if you remember in our filter designing class, by the placement of poles and zeros we discussed that what happens, the high frequency noise components, they will be amplified because there is nothing over here. Okay, now 3 point the central difference filter, this is the equation. So over here you will be having two zeros, so it will be allowing the high frequency components, but at the same time the high frequency noise components, they will be suppressed. Okay, similarly to the least square polynomial smoothing filter, we have least square polynomial derivative approximation. Again the similar thing. Again, if you see the weights positive to negatives we are having. Okay, so these are also basically the gradient filter. Then second derivative filter, if you see what we are having, this component, it is getting multiplied twice. Okay, so if you apply uh, three of such thing, and if you multiply it with another one, 1 minus e to the power minus 2, it will become third derivative filter. Okay, so again, why it is used? Because when you try to use this 3 point central difference filter, the high frequency, the high noise frequency components, they are not getting amplified. Okay, they are not getting amplified, and that is the advantage why we are not using 2 point difference filter for designing the second derivative filter. Rather, we are using this 3 point central difference derivative filter for designing the second derivative filter, because you are using the derivative filter, first order derivative filter, twice. So twice, when you are using it twice, what does that what it will do? If you are using the 2 point difference filter at the initial stage, it will increase the amplify the noise. Again, that noise will go to the second stage, again it will be amplified over there, further amplified, right? So you will be getting more and more noise component, which is not desirable. Okay, so with this we complete this thing. We discussed, I told you that we will be designing this notch filter. And how will you design it? Because in India, your power line signal component, it is say at this power line is being distributed at 50 hertz. Okay, so if there is a 50 hertz noise, how will you design the notch filter over here? Bola, your fs is equal to 180, and you have to suppress the 50 hertz noise. How will you do it? How will you design the filter? 180 hertz is 2 pi. Hmm. फिर you are interested in 50 hertz, कितना होगा? तो निकालो कितना होता है? 5 pi by 9. ओके, कितना डिग्री हो रहा है? ओके चलो, इसका 5 pi by 9 एंगल में तो आया ना ना? ये क्या है? 2 पाई है. इट इज समवेयर ओवर हियर. 9 ना? 9 5 45, 0.5 पे, अराउंड पाई/2 के आसपास यहाँ पे कहीं पे आ रहा है. यहीं पे कहीं पे आएगा, राइट? So if it is coming somewhere over here, हाँ, तो इसका ये z का इंफॉर्मेशन क्या है? जीरो कहाँ पे बैठेगा? इसका पोजीशन क्या आएगा? हम्म। कौन सा? हाँ वहाँ पे जीरो आएगा, वो पॉइंट निकालो, पॉइंट निकालने के लिए बोला है। अरे जेड में, जे में कॉम्प्लेक्स, कॉम्प्लेक्स डोमेन, लाइक दिस वन, फाइंड द लोकेशन ऑफ दिस थिंग। ये कितना है, पाई बाई टू है, उसके बाद आपका एक सेकंड एंगल ज्यादा है ना, वो एंगल का वो निकालो कितना आ रहा है। निकालो। और देखो, आई डोंट नो, फाइव बाई एटीन आया, सो दैट इज योर, तो आपका क्या रहा है, व्हाट यू गॉट, राइट एंगल ट्राइंगल यू गॉट इट, ये थीटा आपको मिल गया, तो ये वाला निकालो, ये वाला निकालो, एक परपेंडिकुलर और इसका ये, वो तो वन है, यू हैव वन, यू हैव द हाइपोटेन्यूज, यू हैव दिस थिंग, हाँ निकालो उसका, 0.99, 0.17 ये आया, सो यू आर हैविंग 0.17 प्लस माइनस 0.99 J. So what we discussed in our filter filter designing by placement of poles and zeros, we will only be considering the upper part. So our zero location is 0.17 plus 0.99 J. Okay. So your transfer function would be, क्या होगा, xz is equal to z minus location of the zero, right? So this is your original transfer function. You can also again say J Z inverse. क्योंकि उसके नजदीक है, उसी के आसपास आएगा, वन से कम होगा थोड़ा। 99 हो, 98 हो, समथिंग उसी के आसपास आएगा, वन के नजदीक आएगा। 98 हो तो भी 0.98 होगा। फोर, फोर को लेके तो आप ये नहीं करते, राउंड ऑफ नहीं करते, तो 0.98। यू विल बी गेटिंग दिस काइंड ऑफ क्वेश्चन। ठीक है, डिजाइन योर ओन फिल्टर, नॉच फिल्टर बनाओ, हाई पास फिल्टर का मुझे यहाँ पे कट ऑफ फ्रीक्वेंसी चाहिए, एंड यू हैव टू डू इट, सो यू कैन नॉट एस्केप फ्रॉम देयर। तो बेसिक आपको अगर नहीं पता है, देन यू विल बी ए डेड फिश। हाँ, then you have to find out the phase response and amplitude response. I told you that the designing of the filter, Hz is equal to Z minus, it was I think 0.17 plus J of 0.98. right? So this was the transfer function I told you, and I was waiting for your responses. This shows how sincere you people are. While designing the filter, what was the first criteria I told you? There were some criteria where I discussed. What were the criteria? All poles should be within the unit circle. Zeros can be placed anywhere, right? Then another was number of the poles should be greater than equal to the number of the zero. So यहाँ पे तो only we are having zeros. Where is the pole? Is it a realizable filter? It is not a realizable filter. So okay, so what it should be? It should be this thing z minus 0, that means z. Okay, so what should be your transfer function? It should be 1 minus 0.17 plus j 0.98 z. Okay, sorry, z inverse. So this should be your transfer function. Now if I ask you to find out the amplitude response and the phase response, कैसे निकालोगे? The first and foremost thing is that you have to put something over here. What is that? A to the power j omega. So first should be 1 minus 0. A to the power minus है ना, minus j omega. Okay. So we are interested in that phase. So again, what you have to do? Take out the real one, imaginary one. Again, you will be having some multiplications going on. So after that, again you have to find out in the format of a plus jb. So once you have done that, then you will be able to find out the amplitude and the phase responses. Okay. Now, uh, for you today, you do this numerical. So first of all, in our last class, we have seen about the low pass filter, how it can be designed by the frequency sampling method or Fourier transform method, whatever we have discussed. Okay, we have discussed about the low pass filter. Now you have to do the numerical about the low pass filter. So find out all the coefficients, then find out or compute the Hanning window coefficients for order n equals to 10. Then compute the filter coefficients of the high pass filter whose specifications are given in question 1. Okay, by employing the Hanning window. So after that, from here you will be getting the hz, and then you have to realize the filter and determine the frequency responses for both magnitude response and the frequency response. Okay. So here I have broken down into 5 components. In exam, it is a single. It will be a single question.